Now with that said, let's go on and do some quantitative work. The way we'll approach the quantitative aspect is, first of all, I'll address the advective transport in the system. And we'll do that using Darcy's law. And then I'll couple advective transport and diffusive transport together by looking at the transport of a long-term transport of a conservative tracer. And then from there, we'll go on and couple on geochemical reactions to look at the major ions. As far as advective transport goes, what we need is we need porosities for these materials, hydraulic gradients, and hydraulic conductivities. Porosities, we measured numerous porosity numbers, and they were all very consistent. The porosity in the till is 0.32. The porosity in the clay is 0.40. So that was one of the three parameters we needed to measure, to calculate advective transport hydraulically out of the way. The second point is we needed hydraulic gradients. We obtained those from our water level data. As I mentioned earlier, our water level data below 30 meters for all our piezometers still have not reached equilibrium. The ones above have. These are representative data for the piezometers, representative recovery data. Again, the spikes are the result of sampling. What you can notice is the very shallow one, the brown one, is in the oxidized and fractured till. And you can see dynamic flow up there. You can see every spring the water level rises to at or near ground surface, then drops throughout the remainder of the year. Again, then drops. This is a result of the spring recharge. Waters in this oxidized and fractured zone are all tritiated. All waters collected below that are non-tritiated, are below detect. The two piezometers that are completed in the till, the pink and the lime green, those are representative of the till responses, and you can see that they are very similar. Slow responses, low hydraulic conductivities. Compare that to one of the responses for the clay aquitard, and that's the yellow recovery. Ultimately, that yellow recovery when it comes to equilibrium, will be less than 2 meters below ground surface. So it still has a long way to go. A much lower hydraulic conductivity for the clay aquitard than for the till aquitard. Over the last 5 years since installation, the piezometers in the clay aquitard have responded to the tune of 10 meters. So they're responding very slowly. Hydraulic gradients. Well, how do we calculate hydraulic gradients? I mentioned earlier we used the Christensen data, which was monitored every month since 1986. We used that data, and we used our shallower than 30 meter data, coupled them together, and obtained an estimate of hydraulic gradient. The hydraulic gradient in the till is downward. It's downward at 0.014, and in the clay, it's downward, wouldn't expect that, at 0.6. So now we have two of the three parameters we need out of the way to calculate advective transport. The third one, the hardest one, hydraulic conductivity. We looked at it in a few ways. We started off by looking at hydraulic conductivity of samples brought to surface, taken back to the lab, analyzed geotechnically, odometer consolidation, falling head, triaxial testing. And these are the results of our lab numbers. You can see that they are fairly consistent. The numbers for the till are in the order of 2 times 10 to the minus 11 meters per second. The numbers for the clay the mean number is about 4 times 10 to the minus 12 meters per second. Very low hydraulic conductivity. We looked at recovery of the piezometers, and these are our results. Bearing in mind that below 30 meters, we had to approximate where equilibrium was for those water levels. Accounting for that, the error in the data point is not that great. Below 30 meters in the till, the numbers are within a factor of 2 of each other, and the typical numbers are in the order of 4 times 10 to the minus 11 meters per second. The numbers in the clay are very representative of what we measured with the lab testing results. Because with the lab testing results, we were very close to the lower limit of measurement using those techniques, we went about it another way and tried an inverse method to obtain the hydraulic conductivity of the clay aquitard material. We did that by knowing the hydraulic conductivity of the till, the hydraulic gradient in the till, and the hydraulic gradient in the clay aquitard material itself, and we calculated the hydraulic conductivity. That hydraulic conductivity meters per 10,000 years downward. These numbers for hydrogeology are extremely low. On terms of geologic scale, they're not that great, but hydrogeologically, they're very low. So what does that mean? Well, let me summarize our hydrogeology or advective transport calculations. There's the calculated velocity. Now, if we were to look at residence time based on that velocity, it's several tens of thousands of years in the till itself. Well, as I mentioned earlier, the till was deposited less than 30,000 years ago. Put those points together, and our postulate was that this till should contain glaciogenic water at some point in its depth. At some point in its depth, it should contain water deposited with the tills, when the tills were deposited by the glacier. Okay? So, two things I'd like you to keep in mind. One is the velocity we've calculated, and the other is the fact that we should have glaciogenic water in the till. Now let's go on and couple the advection and diffusion together and look at it using a conservative tracer. So we're interested in a conservative tracer, long-term conservative tracer, naturally occurring conservative tracer, and we have any number of them to choose from. We could do chloride, we could do chlorine isotopes, we could do boron, we could do boron isotopes, we could do oxygen-18 deuterium on the water molecule. We've done all of these. The information I'd like to present to you is based on the oxygen-18 and deuterium of the water molecule. And I've selected that because, in my estimation, it's the most conservative of all the tracers that we hydrogeologists have available to us. So the first thing we did, every time we collected a water sample for chemical analyses or any analyses, we put a sample aside for oxygen-18 deuterium analyses on the water molecule. Putting all these data together, the deuterium number and the oxygen-18 number, if you're not familiar with the units of these, just assume they're concentration units. You plot these data together, and they fall in a straight line. They fall in a straight line that approximates the local meteoric water line. This is measured in Saskatoon, the city where I'm from. What one can say about these data is that any trends that we observe with depth with deuterium or oxygen-18 in these Aquitards cannot be the result of evaporation and cannot be the effect of exchange reactions. The only explanation we have available to us to explain any shift in these data with depth is mixing. Mixing between isotopically enriched and isotopically depleted water. So please bear that in mind. Now I'll present to you the data. But before I do that, let me just tell you that because of the linear relationship, the meteoric water line relationship, we'll present the deuterium data. And I will not present the oxygen-18 data, but we can assume fairly easily that what happens to deuterium also is reflected in the oxygen-18 because of the linear relationship. First thing we did was, of all these water samples we collected, we plotted deuterium from the piezometers with depth. And these are mean numbers. In the Aquitar material, the size of the dot hides the error bar. So we have very tight control, invariant again with time with regard to these isotopes. In the oxidized zone, the upper few data points, the error bars are quite large because of the dynamic flow in this system between spring and summer. We couldn't just use these data, although it's a very pretty picture, we couldn't just use these data because we had a lack of data down in the clay, and we needed data from the clay. So we obtained this information using radial diffusion cell testing on core samples. And these are the results of radial diffusion cell testing to obtain deuterium analyses. It complements the data very nicely, except for one anomalous point, which I believe is just that, it's anomalous, the one at about 38 meters. The next step that we looked at was that boundary between a till and a clay was very critical to our interpretation. We were concerned that we didn't believe that there was any permeable zones or any problems with dealing with the interface as a sharp interface, but we felt we had to prove it, so we went back and did additional coring across the interface and collected core samples and used an equilibration technique to obtain the deuterium values, and these are the results. So we have a very well-defined depth profile for deuterium. From this profile, you can see three end members. You can see the end member at minus 136 up at the top of the unoxidized zone. You can see a minus 178 between 30 and 46 meters below ground surface. And you can see another end member down in the clay Aquitard itself and that being minus 144. Bear in mind what I told you about the plot between oxygen-18 deuterium. What we're observing should be the result of mixing. We observe mixing between all three end members. Now, what's the source of these end members? Well, the upper one, the minus 136 up at the top, that is representative of atmospheric input into the system since during the Holocene period after deglaciation. It's also representative. It's the exact same number as the mean weighted annual precipitation for Saskatoon. So that input up there occurred in the Holocene period. The very negative numbers, the minus 178 that we observe in the heart of the Till Aquitrd, those numbers, if we were to calculate a temperature of recharge from those, and one can do this with these data, the temperature of recharge of the water that exhibits the minus 178 signature, the recharge for that water indicates that that water was 8 degrees colder than present day. We have a number of other lines of evidence, but I'll stop there and just say that we attribute those very negative numbers to water that was introduced into the Till during glaciation. Okay. The other end member, the minus 144, we have no explanation for it. It's not water that was present in the clays during the clays deposition as part of the Western Interior Cretaceous Seaway. But it's had 70-odd million years to obtain that signature. What was attractive to us, however, was the fact that it was a fairly consistent signature at depth. So what do we do with these data? Well, the next step is I've convinced us all that we can deal with a one-dimensional system, so we'll deal with one-dimensional equations. We'll couple advection and diffusion together. To do that, however, we need an effective diffusion coefficient in these aquitards for deuterium. We also need an effective porosity for deuterium in both of these aquitard materials. And with those parameters, if we can measure those parameters, then we can go ahead and determine what-if games. We can obtain a best fit between simulated data and measured data for different velocities and for different transit times.